My name is Charles Eller, welcome to my Physics 2 Lab 6 Magnetic Molasses Lab. Some of the concepts we have to know for this lab include magnetic field of a bar and a magnet, which is shown in the equation to the right, magnetic flux, which is known as the integral of magnetic field dotted with n hat change in area, with no Faraday's law, which is shown right here with EMF equals the absolute of the derivative with time of the magnetic flux, and Lenz's law attached to that, which is just the negative of that. We also have to know Ohm's law, which is EMF over R, or also just the absolute of the derivative of the magnetic flux. We have to know the magnetic force on a loop. We also have to know the momentum principle and then the gravity, the force of gravity as well. So you look to the right, you can just see a general diagram of what a bar magnet will look like falling through an aluminum tube, which is what we're measuring in this lab, and just seeing the effects compared to dropping it in free space versus the tube. And we can see that the magnet is applying like a brake with a force due to the aluminum creating some type of induced current, which is also the idea of Faraday and Lenz's law. And the overall net force is downwards because gravity supports a greater value compared to the magnetic force. And then some of the things we had to know about the tube: the length was 0.32 meters, width was 0.006 meters, the inner radius was 0.02 meters, the outer radius was a combination of the width and inner radius, so it's 0.026 meters. The mass of the bar magnet was 0.024 kilograms, and the magnetic dipole moment of the magnet was 3.206 newton meters per T. The average time it took for the magnet to fall with a length of 0.32 meters was 1.26 seconds. However, according to the code, it was supposed to be around 1.32 seconds, so that could just be more of a human error for that difference. Some concepts or checkpoints we have to know while we went through the lab was why can't we use a ferrosis tube, for example, a steel pipe? And a ferrosis tube contains iron, which may interfere with the falling magnet because of the induced magnet that is created. So the magnet might stick to the side of it rather than just falling all the way down. And what happens to the magnet? How does it compare to a magnet falling in free space without a tube? As I mentioned before, with the braking occurring, the magnet falls much slower in a tube compared to free space, which contains no tube, because there's no braking that's occurring, so there's only gravity going downward on the tube. And we have a lot of code to go through. The step one just included the initial stuff about the tube. Step two just included the basic stuff about dipole, so the R mag, R hat, and then the B, which is just using the equation I mentioned before, and just giving overall setup for the actual experiment. Step three was just finding stuff about the radius, distance, speed, and then trying to find some type of ratio or to the equation just to find the dFdt, which is a change in force with time. And then step four finds the current of the ring, which is just talking about the negative of the deflux, which we just found, divided by the ring's resistance. Then step 5 and 6 go into the force at the ring, which is just these equations I mentioned before as well. And then we found the force of the magnet, which is combined the force of the magnet and the force of the ring. And then the F net is the force of gravity plus the force of the magnetic, which we know that the gravity is greater than magnetic, so we know that the overall net force is slightly downward. And then we can also just, with step 8, find the bar magnet's velocity of position over time, which we use to find this graph, which gives us the velocity over time. And we can see right when we dropped the magnet in the tube, it had its highest peak in it actually falling. And then once it got settled inside of the tube, it stayed constant right until it left the tube. And we can also just see that the average time, the computational time within the tube was 1.32 seconds, was only 0.06 seconds off the actual experiment we did. We have some what ifs. What if there is resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? And as the resistivity reaches zero, and the upward force the magnet creates increases, and soon results in the magnet having a greater force upwards than gravity downwards, stopping the magnet from falling down the tube. And then what if holes or slots were cut into the tube? How would it affect the ring's current in your model? It is possible that the cuts would cause the currents in the tube to not be able to create as good braking force for the magnet, and the magnet would fall as if there was no tube surrounding it at all, just because us cutting holes kind of stops the current from being actually able to be created between the magnet and the tube. So it's just like we're falling into free space. Thank you.